Okay, so we are in office hours for, what is it, week 7?
Yeah.
And we got a whole bunch of problems that we're going to go over. You can take my chair if you want to. We're going to look at quiz 4, number 5, which is this problem. Is that the hydrogen atom problem?
I think it's Rydberg.
Yeah.
Rydberg equation. That one again. I'll tell you, you're all in office hours. I don't know how many people watch this, but it was still like 40% correct on last week's quiz. You know, I'm not going to say what that means, but you all know what that means.
I just don't like.
So let's go ahead. Let's go ahead and pull up your number and let's look at your specific values and see what we can do.
So an absorption of 1.9447 times 10 to the third nanometers raises an electron in a hydrogen atom from n equals 4 to what final n?
Okay. So people already said kind of what's going on here, right? I just wrote down the important things. Actually, I missed one of the important words. What was one of the important words? Absorption. Why does that matter?
Yeah.
It means it's going up. So that means when we solve this, if this is our n equals 4, put another line in there, this has to be going up to something. So this number, right, this number without getting into all implied, explicit implied thing, we know that this number already has to be 5, 6, 7, 8, like something bigger than 4. So people who are solving this and getting answers of 2, some people put 4 in again, doesn't make sense. Right? It has to be bigger because it's absorption. If it was emission, it'd have to be smaller. Right? So that's the first piece of information. If it was emission, it'd be 1, 2, or 3. Right? And we'd be able to kind of like guess and check. Do the calculation 3 times with each thing and see what wavelengths we get. Now, in this situation, we've got 3 different things that we're thinking about. We've got our energy of the photon is equal to hc over lambda. We've got our change in energy of the atom is equal to negative z squared rh 1 over n final squared minus 1 over n initial squared. And then we've got the important energy of the photon is equal to the absolute value of the change in energy of the atom. And I think this last bit is the one that really messes people up, because it's that absolute value that messes people up. Especially for this one. I switched it. The other ones have been emission, and this one I switched to absorption. I think that messed with people. But let's talk about how we deal with both situations. So first thing we can do is we can use that first equation to calculate the actual energy of the photon. I have my wavelength, so I can do 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8th divided by 1.9447 times 10 to the 3rd times 10 to the minus 9, because nano is 10 to the minus 9. I can just put these two things together, and that's just going to be a 10 to the minus 6. So I'll put those two things together, the 10 to the 3rd and the 10 to the minus 9. It's going to be a 10 to the minus 6. Plug that all into my calculator. 6.626 times 2.99 divided by 1.9447 times 10 to the minus 6. And I get a photon energy, I'll write it down here so I have more space, 1.0188 times 10 to the minus 19. Okay. Now I can go ahead and do this part. I know my z value is equal to 1. I know my n final is the unknown thing. I know my n initial is 4, so this is going to be minus 1 over 16. My Rydberg constant is 2.18 times 10 to the minus 18. And I've got a problem here, right? I can't just solve this and like make the negative disappear, because what if this parenthesis is negative, right? And this is the part that messes with people in the absolute value. and this is where it was easier when I gave you the two n values and you could solve it. If we could calculate the energy of the atom was positive, it would just be positive and we're good. If we calculated the change in energy of the atom was negative, we just drop the minus sign and we're good. In this situation, I know the change in energy of the atom should be positive. I know that my n final has to be a bigger number. So let's just do a quick little check, because this is what messes with people. This absolute value sign does not get rid of the negative in this case. Why? Well, let's just do a quick check. If this was 1/25 minus 1/16, what would we get? So this is like from 4 to 5. 25 inverse minus 16 inverse. That gets us 2.25. Oops, let's put our 0 in there. Right, that's going to get us negative 0.0225. This negative sign outside would cancel the negative sign from the parenthesis. And so the energy of the atom ends up positive, and we don't drop the negative sign when it ends up positive. Right? Because this is absorption, the parenthesis is always going to end up negative. And then I need this negative outside to get rid of that negative inside. So the absolute value here doesn't get rid of the negative outside because the parenthesis is always going to be negative for absorption. I keep dropping my calculator. Come on in, there's another chair in here if you want to scooch in.
So what you're saying is that when it's asking for absorption, the negative stays in the Rydberg equation, and then emission, the negative goes away?
For this absolute value part, right? And we have to be careful, and that's why I'm doing this kind of like little, we have to think about what's that absolute value going to do? The absolute value is going to make the overall atom energy end up positive. But if I get rid of this negative sign, that negative sign was already going to make it end up positive. So if I drop that negative sign, I'm actually ruining what was already going to happen. Question?
Will you ever have a correct answer that's negative? And in that case, should we ever really...
An n value that's negative?
Well, I'm talking about the absolute value sign, making it so that we don't have that negative energy value.
Anytime you have emission.
Oh, okay, sure.
Right?
I just didn't
The
think there'd be
opposite,
negative
like,
energy.
it's the, you would never have a negative, the atom energy could be negative, right? The atom can gain energy or it can lose energy.
Yeah.
The photon energy always has to be positive. That's why the absolute value is around the atom, not around the photon.
In that case, should we always think of just it being positive, or could it just not be positive and just be negative? Like, because you just said the energy of the photon can't be negative, so
Correct.
we just always think of it as positive? If we
The
can?
photon energy, yes.
Okay, sure.
The thing that's messing people up is dealing with this absolute value, and do we get rid of that negative? Because you can't just erase that negative sign and be like, it's positive now, because this part is negative. And so you're erasing that negative sign actually makes the whole thing overall negative, not positive. So you have to think about all the different math steps going into it to make sure you're correctly making sure that energy ends up positive overall. So here's a way that you can deal with it when it is absorption. And that is bring the negative sign inside here. So one of the things you can do, can I give myself space for this? Let's see here. I'm going to erase this bit here just for a moment. So one of the things you can do is you can bring this negative inside. So it is 1 times 2.18 times 10 to the minus 18 times 1/16 minus question mark, right? That negative sign comes in, it flips the order. Now that whole thing is going to be positive. And we don't have to worry about the absolute value. Because it's absorption, and this question mark is always going to be a smaller number than the 16th, right? So there's a lot, and I mentioned this the first time, there has to be some thought process there. There has to be some logic where we consider, is it absorption, is it emission, is the atom gaining energy or losing energy? How does it relate to the photon? You have to be able to think through that kind of what's physically happening aspects to make sure the math matches reality. Is that what messed you up?
Yeah, because I got an answer that was smaller, and I was like, I know that's not right, but I was like, I don't know, I didn't realize that. I think I just dropped the negative.
Yeah, when people see that absolute value, they think drop the negative, but they forget that there's like there's two parts that might be negative. And whenever you have absorption, this parenthesis part is negative, and it's going to get rid of that negative already. So when you drop that negative, you're actually introducing a negative. And it's like, right? So there's thinking about the different parts of what's going on. And for me, I have I'll be honest, I have a hard time thinking about all of that. That's why I did that 1/25th thing. Like, part of the way that you can solve this problem is to just say, well, I know it's going to be 5, 6, 7, 8, or 9, or 10, or 11, 12, or it's going to be some value. I just try a couple and see how it goes.
That's
Right,
what I
but
had
for
to
me, it's like I always like to slow down and be like, well, I have a hard time thinking about like question mark minus 1/16. So I think, okay, well, what if n final was 5? What would happen in that case? What if it was 6? Whether it's 5 or 6 or 7, that thing always ends up negative. So I just go ahead and bring that negative in. So now this part's positive. 1/16 minus 1/25 or 1/36 or 1/49, that's always going to be positive now.
So do you have to, like, is this just an easier way to do it, like making it positive and flipping this, or is that something you have to do? Like,
No, that's
or
just
can
an
you just
easier
keep
way
it
to do
negative
it.
and keep that one?
You can keep both negatives as well. That would also work.
Okay.
I find the reason I like to do this is because people always try to erase the negative sign when they see the absolute value.
Yeah.
Right? And so for me, just forcing it to be positive is what's safer.
So
now there's no negative sign to drop.
my thing was, like, when I was solving those equations, I do this like the very last, like you solved it and then put it into the problem. Like I would get rid of I'd get rid of the, what is that called again? The
Rydberg constant?
Rydberg constant, and divide it with the,
Yeah, so let's keep going.
divide it with the change of energy, and then is that a good way to do it
That's
too?
totally fine, right?
Okay.
So let's go ahead and keep going through this problem. So now that I've got rid of that, the absolute value of this thing, since I've already guaranteed that it's positive, is also going to be positive. So, I just erased my number. What number did I have written
It
there?
was 1.088.
Times 10 to the minus
19.
Okay, good. Is equal to 1. I'm not going to worry about 1 squared anymore, right? Because that's technically 1 squared, which is just 1. 2.18 times 10 to the minus 18 times 1/16 minus question mark. Well, let's call this question mark what it is now, because I'm close enough to finishing it. 1 over n final squared. Right, and the order of the final initial switched because of the way I moved to the negative side.
Wasn't there a 1 before the 8? On the,
Yeah, but, over here?
yeah.
Let me double check what's on my calculator. Let's just recalculate, make sure it's 6.626 times 10 minus 34 times 2.99 times 10 to the 8th divided by 1.9447 times 10 to the minus 6. Oh, I got something totally different that time. Let me try that again. Other people calculate help. I don't like hitting it 5 times.
Why does the stuff in the parentheses swap? I forget.
1 second.
Yeah, sure, take it time.
Unless you can help me with this calculation, make sure I get it right.
Yeah.
Okay, I did it wrong again, so.
Let me check, so just real quick.
Trying to do things fast makes me slower.
Yeah. So caption should say, or take all variables.
I got something different again. What'd you get?
I have like a 2 point.
No,
Yeah.
I got, okay. Once more, 6.666. Other people help, please.
Yeah, I'm going for it.
I got 1.018.
Yeah, that's what I got too.
Yeah, that's what I
1.01.
That's what I
Okay.
remember too.
I don't know why I kept getting different thing. Like, I just did the calculation 3 different times, 1.0188. It's like 875.
Yeah.
That's what I got the first time, but for some reason I just keep messing up my calculation now. 6.626. And I don't want to mess that up, so 2.
You don't need sentences. Like maybe add a sentence to say like, for the determination of blah blah blah, and then.
Oh, I got it that time. Okay. I was just trying to go too fast. So, the order flipped because we brought the negative in, right? So, just simple algebra. if we had 5 minus 6, if we had negative 5, right, that would be equal to 6 minus 5.
Sure.
So bringing the negative sign in allows us to flip the order there, and that makes it, so now we're guaranteed. So this would be, and I
Okay,
wouldn't
that makes
just,
sense.
right, so this would have ended up being a
Negative
-1, and then it would have ended up being +1. And now this is just +1. Question?
You only do that with absorption, not emission,
Um,
right? Or can you do it?
The main thing is we have to keep track of the negative signs. We have to pay attention to the energy, the change in energy of the atom being positive or negative. And the reason that becomes this extra problem that everyone's struggling with in this case is because the change in energy, because this is energy going up, we know the change in energy of the atom is going to end up positive when we finish this calculation. So that means if I'm looking at this part where I've got energy of photon equals delta E of atom, I shouldn't change the sign of the energy of the atom at all, right? Whatever it is, it's already going to be positive. The thing that people are messing up on, it's just an algebra thing, which is like, this is supposed to be a chemistry thing, but it's algebra that's messing people up, is when they look at this equation of negative z squared times RH times 1 over n final squared minus 1 over n initial squared, they look at absolute value and they're like, oh, get rid of negative. That's what absolute value does. But it's like, this thing is also negative. So you have to keep track of this part's negative and this part's negative. So it's going to end up positive already. We don't need to get rid of any negative signs. Absolute value doesn't mean just drop negative sign willy-nilly. It means once you have a value, you drop the negative sign. Our value is going to be positive because it's absorption. Right? There has to be that thinking about what's physically going on, what are we representing. Since we know that it's absorption, that negative sign has to stay put, so it gets rid of that negative sign and ends up overall positive.
So does that mean that basically you either have to keep both of them positive or both of them negative? It just can't be one or the other?
Correct.
Okay.
Correct. And back to your question of, is there one thing we do for absorption and another thing we do for emission? Ultimately, yes. Right?
You could
because
flip-flop either
this
way.
parenthesis will always end up negative for absorption, and this parenthesis will always end up positive for emission. So for absorption, this whole term ends up positive because it's negative and negative. And for absorption, for emission, this whole term ends up overall negative because it's positive and a negative. And so we have to pay attention to the fact that absorption and emission are two different processes. We have to pay attention to not just the negative sign that's out front, but also the negative sign from this, the potential negative sign from the subtraction.
So then, rather than flipping, can you just look at your photons and be like, oh, I got a negative number for this. I'm just going to make my Rydberg constant negative. So
Yes, right? There has to be some logical processing in there, though, right? And there's, if you've read along in the textbook writes the equation slightly differently to essentially guarantee that the parentheses is always positive, but then it only works well for emission. It doesn't work well for absorption. Because it gives this guaranteed of order. So at this point, let's go ahead and finish this problem. We've got our logic. Are we good with the logic in blue? Right? We have to have some logical thinking about where our negatives are coming from and our positives are going. I got rid of my negative not by dropping it, but just bringing it inside the parenthesis to flip that order. That's a fine way to deal with it. Then I go ahead, I divide over. I lost my calculator. I divide over, I got my 1.0188 times 10 to the minus 19 divided by 2.18 times 10 to the minus 18, and I get 4.673 times 10 to the minus 2 is equal to 1/16 minus 1 over n final squared. The way that I go through the algebra here, there's a lot of different things people try to do. I'm going to add subtract to opposite sides. So I end up with 1 over n final squared is equal to 1/16 minus 4.6 Yeah, 673 times 10 to the minus 2. And I'm going to go ahead and calculate what this side over here is. Negative plus 1. And I get a value of, I'm just going to continue over in this box. So I get 1 over n final squared is equal to 1.5766 times 10 to the minus 2. I crisscross, so I end up with 1 over 1.5766 times 10 to the minus 2 is equal to n final squared. Inverse that number, and I get 63.5 is equal to n final squared. Take the square root, I get about 8. Now, the way that I would set this up and do it would be a lot quicker. I was doing a relatively slow walkthrough because I know there was a lot of mathematical confusion there.
Would you get the same result if, before you did all that, if you just added 1 over 16 to the energy?
You would have to subtract it over. And then you'd get a negative over
yeah,
here and a
that's
negative
right.
over here. I don't like it when I get negatives. The other thing you can do, let's say you go through all of this and you're like, I got 8. Is that right? How could you check? What's it? Yeah, plug it in. Right, I can come back up here and I can see if I get my change in energy atom correct. If I get this value, if I plug in 1 over 8 squared there. So I do 16 inverse minus 64 in, oops, not that. 16 inverse minus 64 inverse times 2.18 times 10 to the minus 18. Oh, I did 8. Okay. 16 inverse minus 64 inverse times 2.18 times 10 to the minus 18. What am I doing wrong here? 16 inverse 64 inverse times 2.18 times 10 to the negative 18. There we go, okay. And I get 1.02 times 10 to the minus 19, so a little bit of rounding, but close enough.
Is that generally a good tactic to just continuously plug in the numbers, especially for emission?
I would say no. I mean, for emission, it's a little bit easier because you've got less options.
Yeah.
For absorption, definitely no, because you've got an infinite number of possibilities.
Would you?
But what I would recommend is after you go through and you've got an answer, you can double check if that answer is correct by plugging it back in to see if it's self-consistent. That's essentially giving you a way to make sure you didn't make a calculator mistake or make a logical mistake in your negative signs.
Sure. Would you give us a jump that goes to double digits, or?
It's possible. It's not that great though, because I draw these lines getting closer and closer to each other on purpose, right? Because it's 1 over n squared. So if you were going from like n equals 4 up to n equals 20, 20 to 21 are so close to each other that it could be a rounding error difference. And so I'd really like to steer clear of those really high values. Even between 8 and 9, I bet it gets close to like rounding error differences. Because the difference of 1 over, like if you had 1/16 minus 1/64 versus 1/16 minus 1/81st, probably pretty close to each other.
Gotcha. And also, probably, I don't know, it's about the exam, it's cumulative, right? Or is it just going to be covering our latest material?
Previous exam or?
No, this.
Oh, sorry, I was focusing on
Yeah,
problems.
it's a side topic. My bad.
Okay, so let's first finish this
Yeah,
problem.
sure, we can finish it.
Are there any questions about this one? Are you feeling okay about it?
I just have one more question.
Sure.
When you go back, you get the answer and you plug it in. Does it matter if the Rydberg constant is negative or positive at that point?
No, we want to plug it back into like this thing, right? We want to plug it back into our original Rydberg equation. We know that the change in energy of the atom should be positive, so if you get a negative value here, we already know we've made a mistake. If we get a positive value here, it should be equal to our photon energy if everything is self-consistent.
Okay.
Other questions? Okay. So that was quiz number 4. That was quiz 4, number 5. We've got a lot of other questions to get through. Quick while I'm erasing the board, midterm is cumulative-ish. All of my midterms are cumulative-ish. That is because it will focus on the new material, but the new material also depends on old material.
Okay, sure.
So we can't just do Rydberg problems. I originally would say I'm definitely not going to do a Rydberg problem, but we'll see how it goes on this quiz before I say that for sure.
Sure, and I don't know, this might be...
I mean, it may or may not be on this next quiz, sorry.
Gotcha. Where can I find this in, like, Canvas? I don't know if it's just me not being able to see it, but I can't find, like, a due date for the exam. Like,
Oh, I probably haven't put it in yet. It's Thursday next week.
Thursday? Okay,
Yeah.
Gotcha.
Online portion is Wednesday, just like last time. In-person portion is Thursday, just like last time.
Gotcha, sounds good.
Yeah, and I usually only do due dates a week out because people see too many due dates and they get confused about what they're supposed to work on.
Fair enough.
Okay, so that's quiz 4, number 5. Let's look at 5.1, number 31, and the idea of formal charge.
I don't need 31 anymore. I figured
Okay.
it out.
Cool. What was it though? Was it about
It
formal
was
charge?
it was an isomer with an ester, but I messed up the hydrogens.
Oh,
That's what
okay,
it was.
great, okay. So let's go ahead and talk a little bit about formal charge and how we can tell if we're getting a good Lewis structure or not. And formal charge is, again, one of those things where when we're drawing Lewis structures, we don't need formal charge most of the time, right? If we're doing ester, what was it an ester of? Do you remember what it was?
It was C6H10O2.
Right, if we're drawing something like this, we can use kind of the pieces we learned before, where ester or ether? Ester?
Ester.
1, 2, 3, 4. 1, 2, 3, 4. Let's see here. Let's put a break here. Extra carbon there. O. 1. Oh. 3, 4, 5, 6, 7, 8, 9. That's too many. Right? 3, 4, 5, 6, 7, 8, 9, 10. There we go. Okay. So this would be C6H10O2. And for this type of structure, I don't really need to do the formal charge calculation on all of it. That has to do with the purpose of formal charge and the fact that I'm using good pieces, right? So this carbon, if I'm looking at this carbon here, I'm going to highlight it. Let's do this carbon here. I'm looking at this carbon here that's got its hydrogen bond in there. It's got the 1, 2, 3 bonds around it. My formal charge on that carbon is going to be 4 minus 0 minus a half of 8. Right, and the formal charge idea is essentially looking at how many openings, that's not enough electrons, there we go, how many openings there are versus how many electrons there are, how many get filled by the end of bonding versus how many don't get filled by the end of bonding. Right, formal charge, rather than doing this picture and having to count like, oh, how many electrons are shared in and all of that, formal charge kind of gives us a mathematical way to more quickly consider that. And it says, look, I start with 4 valence electrons, I should end up with 8 electrons total around, and if it's carbon, that's going to be in bonds. Carbon doesn't like to have lone pairs because of the way that its electrons, the way it needs to share its electrons to get a full valence shell. So formal charge kind of gives us a formal way to do that. And as long as we're working with nice pieces, the formal charge is already set up to be 0. Right? I could do the formal charge on this oxygen as well. Any of these oxygens, I'll do it on this oxygen. It's got its 2 lone pairs. And that's going to be 6 minus 2 minus a half of 4, right, is 0. Anytime I have oxygen, sorry, math is hard, 4, right? Anytime I have an oxygen with 2 lone pairs and 2 bonds, this math is going to work out the same way, whether it's 2 single bonds or 2 double bonds. And that was the good pieces we learned, right? So a lot of the time, we don't need to do formal charge. The good pieces we learned already take care of the formal charge for us and get us that kind of minimized structure. Come on in. If you're comfortable sitting on the floor, you can do that.
There's also a chair under there if you want to.
I don't know why it's under there.
I put it there just because of my wife.
Sorry, could you? Yeah, okay. So the formal charge already takes care of that. No, you can set up right here. Okay, just right in the middle. Already takes care of that type of organization. It takes care of that consideration. So then the question becomes, well, when is formal charge useful? And that's when we're looking at structures that don't use these good pieces. Our good pieces, the good pieces we were looking at, were really only things that were carbon, nitrogen, and oxygen. Those were the ones that we learned. And so anytime we have something that's doing something besides carbon, nitrogen, and oxygen, formal charge might be a good thing to use. For example, if we're doing PO4, 3- phosphate, right? What's the good structure look like? I could draw phosphorus like this. I didn't give myself enough space with that other oxygen there. Hang on. Right? And this could be a fine Lewis structure. If I figure out how many electrons I'm supposed to have, phosphorus has 5 electrons, oxygens, there's 4 of them, that's going to be 6 times 4 is 24, and 3. Math is 29, that's going to be 32 electrons, 8, 16, 24, 32. Looks great. Is this really the most stable structure? And each of my oxygens has 8 electrons, my phosphorus has 8 electrons. First glance, we'd be like, sure, why not? And that's where formal charge comes in and says, well, is this the most stable structure? Are the electrons actually being uniformly shared? And when we do the formal charge calculation, let's just look at it for phosphorus for a minute. Phosphorus has 5 electrons in its valence shell. It's got 0 bonding, and then it's got 2, 4, 6, 8. Sorry, I forgot my half there. Right, that gives me a +1 formal charge for phosphorus. My oxygens in this situation, all of my oxygens are 6 minus 6 minus a half of 2. All of my oxygens are -1s. And the question becomes, is there a way to get more formal charges close to 0? Because there's the 3 things about formal charge, right? Thing number 1, formal charge equals 0 is more stable. Thing number 2, formal charge greater than 1 and formal charge less than -1 are unlikely. Thing number 3, formal charge equals 1 on an atom with higher electronegativity. Right, so in this situation, oxygen has higher electronegativity. It looks like oxygen's got the -1s, but I really go back to this first thing of like getting more formal charge equal to 0. And it turns out that phosphorus, if I could put it in another bond, if I had 5 minus 0 minus a half of 10, that would be better. And so I take off one of these lone pairs, and I put in that double bond, and that's going to make it so I end up with a different formal charge orientation. So I recalculate my formal charges. I'll switch colors for this. My formal charge on phosphorus now is going to be 5 minus 0 minus a half of 10. That's going to be equal to 0, so my phosphorus ends up with a formal charge of 0. This oxygen with 2 bonds and 2 lone pairs ends up with a formal charge of 0, -1, -1, -1. That's going to be more stable. And we talked in class about why phosphorus can have 10 electrons around it. That has to do with the number of valence openings it has being in the n=3 row. Because it can use those d orbitals as well and have up to 18 electrons around it. But it's only got 5 valence electrons to share, so it ends up forming 5 bonds. So in this case, formal charge allows us to recognize a more stable structure. Now, does that other possibility of all single bonds exist? Yeah, but it's less stable. It's less stable. Could happen accidentally for a moment. Might be a more interesting reactive state when you get to organic chemistry. You'll talk about like the next highest resonance structures, like the excited state resonance structures, so they have a lot of reactivity to them. But in this class, we're just looking for most stable situations, as many things as possible, 0, while we're filling the valence shell and we're keeping our formal charges as small as possible, as close to 0 as possible. Did that help, or?
Yeah, I think
Okay.
so.
So, and again, this is something that we don't have to, like, I didn't really need that for this structure. It's only the structures where I'm not using the good pieces, where I can't use the good pieces. My favorite example of this that's like really weird is carbon monoxide, where you end up with that carbon-oxygen triple bond and you're like, this looks really weird. It is the most stable structure, but it's also not stable. It's very reactive. But it's the most stable structure. So that's formal charge. Other questions about that before we keep going?
Do we
go.
have to use the math equation, or are we able to look at the oxygen and say, oh, it has an extra electron that has to be a -1 charge?
What do you mean it has an extra electron?
For example, that oxygen on the very left has 3 lone pairs and a bond, so I can recognize that's unusual. That's an extra
Yes.
electron.
Right, so that is unusual, and the formal charge just gives us a way to like quantify how it's unusual.
Gotcha.
The thing we have to be careful about, and this brings in the idea of resonance structures, is these -1s are not just stuck on these oxygens, they're actually kind of like moving between all of the oxygens. They're not really moving, they're just delocalized, like that double bond is kind of spread everywhere. And so that's where resonance structures would also come in.
Sure. But is it a viable way to not use
Yeah.
math and just see?
Yeah, like honestly, like most of these structures, I don't have to go through the math equation to get the formal charge, but that's because I've practiced a lot.
Sure.
And I know that oxygen missing one of its bonds with an extra lone pair is a -1. So with enough practice, yeah, you can start skipping the equation, but you have to be careful because that's a familiarity issue.
True.
And so when you run into things that you're not familiar with, you got to be careful.
All right. Gotcha.
Okay. Ready to move? Okay. Let's keep going. And so these are the questions we're working on for those of you that just came in recently. We got some concepts to discuss. We've just got a couple more homework problems to do, and then we'll get deep into some concepts as well. If there's anything you want to add to this list, feel free to do so. Just let me know.
Could you add like polarity and like finding if a bond's like polar / where the
Yeah.
it's kind of already like gonna
Yeah,
be
it's going to be related to this.
molecular
Yeah,
shape.
I'll make sure I add that in.
Yeah.
We'll add that in so I make sure I remember to comment on it. Let's look at 6.1, number 27 and number 28. Who wanted those two?
I don't remember who.
I wanted 27. So 27 is the enter the molecular shape around N2O2.
Okay, so we did want to talk more broadly about molecular shape and polarity, so this is a great kind of like segue into those things. So let's talk about molecular shape. Now, molecular shape is one of these ideas that I like to split into 2 steps of thinking, right? And I'm going to rewrite this table real quick. We've got our electronic geometry, and there's only a couple electronic geometries that we worry about. It's linear, which has a 180-degree angles to it. It is trigonal planar, which is 120, and then it's tetrahedral, which is 109.5. And after we have those 3, we've got these kind of subcategories underneath them for the molecular geometry. And we're going to look at it in terms of lone pairs. So if we have, let me switch colors to make it more dramatic. If we have 0 lone pairs, if we've got 0 lone pairs, the electronic geometry and the molecular geometry are the same. I'm going to use TD as a shortcut for tetrahedral because I'm tired of writing it out already. Right? So no lone pairs, it's the same, right? My linear thing is linear, my trigonal planar thing is my trigonal planar, my tetrahedral thing is tetrahedral. If I have one lone pair, I don't really worry about the linear because that's like still the same. My trigonal planar becomes bent, and it's bent, but it's still in the 120 column, so it's a bent 120. My tetrahedral thing becomes a trigonal pyramid. Let me just write that out real quick. Right, and that's the idea. Do I have one handy? Yeah. So that's the idea if I've got my handy dandy molecule. If I take off one of the things, because it's a lone pair, or I kind of like don't see one of the things, I only see where the atoms are, that makes the little, like, it's got a triangle on bottom, but it's not flat. So it's a little triangle pyramid. Right? Then, if we've got two lone pairs, we don't really worry about the linear. This thing only had three things attached, so if we got two lone pairs, it's just like an atom sitting there. That's kind of boring again. And this becomes bent, but it comes bent in the tetrahedral column. That's a bent 109.5. And so we can see the different geometries we end up with. And I always do it in two steps like this. I get my electronic geometry, and then I think, okay, how many lone pairs do I have to think about my molecular geometry? You can also see some pattern in how many atoms are attached. Right? So if I use this green for a number of atoms, 2 atoms if it's linear, 2 atoms if it's bent, 2 atoms if it's bent. How many lone pairs tells us the angle of 180, 120, or 109.5, depending on how many lone pairs are with that number of atoms attached. Trigonal planar and trigonal pyramid, 3 things attached, 3 things attached. 3 things with no lone pairs ends up flat. 3 things with 1 lone pair ends up the little pyramid, that lone pair kind of sitting on top. And then tetrahedral, 4 things. Right? And so it's really just this accounting of keeping track of the different parts to figure out what the geometry is. And when we talk about shape, let's go ahead and call this molecular shape. When we talk about the shape of the molecule, we're really talking about these terms in blue, which are related to the electronic terms, but they're kind of a separate thing. With that in mind, let's go ahead and look at N2O2, shall we? Ready? Is it okay if I erase this?
Can I take a photo?
Yeah.
So with the bottom
Better to write it down too, though.
with the bottom right one where it's bent, that's under tetrahedral. Is that like a relationship between bent and tetrahedral?
Yeah.
Okay.
And that's why it ends up with the same angle.
Okay. Sure.
Right? So if we're looking at, where'd it go? Where'd my molecule go? That's what I get for throwing things. Right? If we're looking at this tetrahedral shape, but I take 2 things off, it just looks bent. But the angle is different. Do I have one of the 109 point? Do I have one of the other ones here handy? I don't have one of the. I don't have the right pieces here to make the other one, unfortunately. I do. Found it. I have to do it right. So these are both bent, but their angles are different. If I try to line them up, it's only off by 10 degrees, but you can see this black one is pointing down a little bit more sharply. So it's 2 different angles. Even though they're both bent, 2 different angles, and it has to do with the parent geometry of how many lone pairs are on there.
Gotcha. So the geometry would be tetrahedral and the shape would be bent?
The electronic geometry would be tetrahedral. The molecular shape would be bent.
Gotcha. Yeah.
And we have to be careful with our language there because some people use geometry. Sometimes they say molecular geometry, electronic geometry. So we always have to have that prefix of like, is it electronic geometry or molecular geometry? I like to use the word shape to kind of create a bigger distinction between the two, but not everybody does that, so we have to be careful.
Sure.
Ready? Okay. Yes, question?
If we had tough, did you do number 26 on 6.1?
On 6.1? So let's go ahead and finish up this one. Let's look at N2O2 and figure out what the molecular shape is. We'll have to keep that chart in our mind as we draw this. So I'm going to go ahead and first I have to draw the correct Lewis structure for N2O2. I like that. Is that right? Why do I like that?
Lower formal charge.
Lower formal charge. I've got nitrogen with 3 bonds and a lone pair. I already know that's one of my good pieces. I got nitrogen with 3 bonds and a lone pair. I already know that's one of my good pieces. Oxygen with 2 bonds and a lone pair. Oxygen with 2 bonds. I picked pieces that are all formal charge 0. I could go through and double check and make sure I've got everything else correct, but this looks good. Then I go ahead and I say, okay, I want to accentuate one of these nitrogens. I'm going to focus on this nitrogen as my central nitrogen with its lone pair and its bonds. How many things, if I'm looking at the electronic geometry, how many things are around that nitrogen if I'm looking at the electronic geometry? 3 things. Right? It's got the lone pair, the bond to the nitrogen, the double bond to the oxygen. 3 things. So if it's got 3 things, its electronic geometry is?
Or not.
You're getting to the next step. Electronic geometry.
Trigonal plane.
Yeah. That would give us the molecular shape. Since one of those things is a lone pair, the molecular shape is? Bent. Right? And most things just specify bent. I find value in specifying the angle of the bend since there's 2 different possibilities. This would be bent.
120?
Yeah. Now, if I did that around the other nitrogen, I get the exact same answer. Right? And so the thing that I think throws people off is when it asks around a central atom. And it's like once you get to these bigger molecules, there's not just one central atom. This has 2 central atoms. This is a central nitrogen, and this is a central nitrogen. When we get to our large organic compounds, there's like 5 central carbons. And we should say the geometry around each of the carbons.
Is that a double bond between the ends?
No,
Okay.
no, that was the green bits was just to accentuate the thing I was looking at.
Okay.
So yeah. There we go. Green bit was just to accentuate where I was focusing.
So when it asks, like, I think that's why I was confused. So when it asked that, like, I would look at the whole Lewis structure, but you only need to target one of the atoms to get the overall molecular shape.
Well, this is, and you'll notice, well, the overall molecular shape is something we have to be careful about with that particular phrase, but just the molecular shape, since both of my centers are the same,
You each do one
one of them. And you'll notice in when we were doing Vesper theory in the lab, there were problems that asked you to report more than one molecular shape because there were multiple. I think it was acetic acid, where it's like, give me the shape, give me the molecular shape around this carbon, give me the molecular shape around this carbon because it's different on the 2 sides. Question?
Is the VSERP theory like what you just drew? That,
Yeah, that's Vesper theory. Right. Also, the thing we did with the strings, right? That strings activity was Vesper theory of like things pushing away and making those shapes. So that was number 27. You want to hit number 26 since we're due with 6.1 number 26? Let's go ahead and do that one real quick since we're right here as well. What is number 26?
It's asking about the permanent dipole moments, like which ones are polar, and then just give you a ton.
Give me a couple.
Okay, so there's SO2 minus 3. Well, I think it's SO3 and then minus 2.
SO3 2 minus. Okay.
And then CO3 2 minus. And then PO4 3 minus. And C2H2. ClO3 minus. And there's like a couple more if you just want to do it.
Let's just start with these. Any others that are really interesting that you like definitely want to do?
I got one.
Yeah.
CH3 CH2OH.
Okay. So this is going to get to the idea of polarity that we also wanted to talk about. It goes nicely with the whole molecular shape thing we were just looking at. And it kind of relates back to the whole idea of the formal charge and making sure we're drawing good Lewis structures. So you can see how it's pretty easy to write questions that incorporate stuff from all of the last 3 weeks into one problem. If we want to go a step further, we can then start talking about which things will precipitate. But let's walk before we start running. Okay, so first thing we have to do with each of these is we have to make sure we draw the Lewis structure correctly so we can get the geometry correct, because we can't figure out if there's a permanent dipole unless we have the correct geometry. If we get the geometry wrong, so for example, if we did SO3 like this and said, hey, that looks good, first off, that's not the correct Lewis structure for it. I didn't do anything in my drawing to commute the correct actual shape of it, and I'm going to get the wrong answer. So we have to make sure we draw the correct Lewis structure first. Some of these I can do really quick, but I'm still going to do them a little bit slower, so I'm going to do SO3 2 minus first. And so we look at this and I say, okay, that's going to be 26 electrons, if I'm doing math correctly. That's going to be 4 times 6 is 24, and then 2, that's going to be 26 electrons. So I'm going to go ahead, I'm going to do my sulfur. I'm going to double bond an oxygen. I'm going to single bond an oxygen. I'm going to single bond an oxygen, a lone pair. 2, 4, 6, 8, 10. Let me count if I've got this right. 8, 16, 24. That would be 26 electrons. That would give me, let me check my formal charge on that sulfur real quick. Right, and this is one of the places where formal charge again becomes useful. I kind of like this, kind of don't like this structure that I've drawn. I like it because I've got an oxygen that's 0. I've got 2 oxygens that are -1. Again, I'm not doing the formal charge calculation for those because I've done it enough that I kind of remember what's going on with those. Hey. But I don't know if my sulfur is actually looking good here. So I'm going to go ahead and do the formal charge calculation on it. It's going to be 6 minus 2 minus a half of 2, 4, 6, 8. Oh, that looks great, actually. So I'm going to have 6 minus 2 minus 4. That's a formal charge of 0. Right, sulfur with 4 bonds in a lone pair is not something we're used to seeing, but it turns out it's actually a stable configuration for sulfur. So, yeah.
Should the oxygen have 3 lone pairs?
Oh, goodness, no. Sorry, thank you. Yeah, that was me getting too excited with lone pairs. And then counting wrong, because that would have been 28 electrons. So now, this is the correct Lewis structure. I'm going to erase this formal charge bit here. I've checked, I've made sure. I already know the other ones. I can put in the formal charge calculations real quick. That's a 0, that's a 0, that's a -1, that's a -1. Notice the formal charges add up to the total charge on the atom as well. So that's nice. But as I drew this, being quick and trying to just get a skeleton structure, I didn't draw it with geometry at all. So now let's go ahead and think about what the geometry around this sulfur would actually be. This is a sulfur with a lone pair, and then 3 things attached. What would be the electronic geometry of that? 4 things total. Think in your mind's eye of that table we had earlier. Or maybe you have it written down. Or it's going to be tetrahedral for the electronic geometry.
And then trigonal pyramid, because there's one lone pair, right?
Yep. The molecular shape is going to be trigonal pyramid. Now, it's an oxygen, an oxygen, an oxygen. We can say that there's a double bond someplace, but really the resonance structure would have that double bond kind of moving around. is there a difference? So now to figure out if this has a permanent dipole moment or not, there's two important things we need to consider. One, is there a difference in electronegativity between the atoms? Two, is there asymmetry in that? Right? So, is there a difference in electronegativity between sulfur and oxygen? Yeah, it's not a huge difference, but those oxygens are going to be more electronegative, which means there's going to be electrons getting pulled away towards the oxygens in each direction. Keeping in mind...
So wait, would sulfur be the most electronegative in this situation?
Why would you think that?
Because from my understanding, the most electronegative, it goes in the middle.
Least electronegative goes in the middle.
Swapped it up.
Yeah. Also, if you just look at the periodic table, what do we know about oxygen?
Second most.
Yeah,
before
so
fluorine.
even before we think about all of that stuff, we should be like, oh yeah, oxygen is more electronegative. Unless there's fluorine here, oxygen's most electronegative.
Yeah.
So the geometry, and because I can't draw three-dimensionally very well, the geometry is going to have that trigonal pyramid shape. Question?
Does the charge on the oxygen make it more or less electronegative? Like,
Remembering back to what we said about formal charge, the charge ends up on oxygen because of its electronegativity, its ability to pull electrons towards it. So it's kind of chicken and an egg. It ends up negative because it's more electronegative, so we can tell it's more electronegative because it's negative. Right? Chicken and an egg.
Okay.
For me, the important thing is when deciding the most stable structure, I could have put another double bond here and made the sulfur negative. But since oxygen's more electronegative, it's more likely to pull the electrons towards it. The more stable structure typically has the negative ones on the most electronegative element. So we typically see those minus ones on the thing that's more electronegative. So depending on which bit we remember first, they loop back on each other for which thing we're thinking about. Okay, so here's our pyramid. The electronegativity is pointing down. Notice because it's got that three-dimensional symmetry, it's kind of got like right, left, front, back symmetry, but it doesn't have top, bottom symmetry. When I look at this, all my arrows are pointing down. So my overall dipole moment ends up pointing down. My sulfur is going to end up, I'm going to draw it really small because it's probably just going to end up a little bit positive. Each of my oxygens end up with a little bit of a negative. Not from the charge, not just from the charge, but from the fact that they're pulling electrons towards them. Right? And again, this is another place where we see that kind of feedback of, well, do they end up negative because they're more electronegative or because they've got that minus formal charge? And it's like, well, they end up with the minus formal charge and the partial negative because they're more electronegative. Again, electronegativity becomes that central idea to all of this, which is back in, was that week 3, where I was like telling you about electronegativity in the last 10 minutes of class, and I was like, this is the most important thing, pay attention. Like, it keeps coming back. Right? It keeps coming back. Question?
So for the electronic shape, the fourth structure are the lone pairs, and that's what makes the tetrahedral?
Yeah, right, but when we're doing them, well, so the electronic geometry, and then when we're doing the molecular shape, we're just caring about where those nuclei are, where those centers of electronegativity might be. So this one, we would say, yes, this one has a permanent dipole moment. Now we have to do that same process again for each of these. Okay, we did SO3. And we're going to number these two. I think I'm going to do number 5 next because it's easier. And someone specifically asked for that one, right? Okay, yeah. So I'm going to do number 5 next. These ones, right, and the reason it's easier, oh, I skipped one, sorry, that's number 6. I'm going to do the 6th one next because it's easier. Why is it easier?
C's, H's, and O's.
C, H's, and O's. I can use my nice pieces to make it. So I don't have to go through the whole formal charge calculation, make the Lewis structure. I already know it's going to use nice pieces, and it's already kind of spelled out how it wants me to make it. It wants me to do a C with 3 H's, it wants me to do a C with 2 H's, and it wants me to do an O with an H. Right? It already spells it out for me. So I can draw the Lewis structure real quick. What did I do wrong with my Lewis structure?
Not
I didn't show any of the geometry. And if I'm not showing the geometry, I'm never going to do step 2 correctly. I'm never going to properly see the asymmetry. So let me go ahead and just redraw this a little bit. I'm not going to erase it. I'll just redraw it, trying to communicate the geometry a little bit better. And it's supposed to look like a tetrahedral here. Right, that's kind of a tetrahedral over there. Then we're also going to have a tetrahedral over here. Let me see, correct angle. We'll put the O over there, and we'll put one H over here, one H over here. If I was trying to do this a little bit better, I would have this, I would have my dashes and my wedges to try and communicate that shape a little bit better. But I've never been really good at the dashes and the wedges thing.
What do the dashes and wedges mean?
They're trying to communicate this geometry. There we go. They're trying to communicate this geometry of things, you know. So like when I look at this, I've got 2 bonds that are flat, then I've got one that's going into the board, and I've got one coming out of the board. So the dots try to communicate the thing going into the board. The wedge tries to communicate the thing coming out of the board. It's supposed to make it look more 3-dimensional. But I'm not very good at it. When you get into organic chemistry and you see how they do this, you're going to be like, oh, that's what he was trying to do? This looks great. I never worked on my art skills enough. So again, here's this one. I've got my 2 that are flat. I've got one going into the board, one coming out of the board. And then my oxygen is going to have its 2 lone pairs and this other H. If I want to do the line angle drawing, it's a lot easier. Right? This would be like a line to an O with an H. That's my way of drawing it. Right? Just do the line angle drawing. Now, to figure out, does this have a permanent dipole moment? We got to correct geometry. Oxygen, very electronegative. It's going to pull electrons away from the carbon. It's going to pull some electrons away from the hydrogen. Right? And I'm going to notice the 2 arrows are kind of pointing towards each other, but they're both pointing up. So I'm going to end up, with an overall dipole moment kind of like that direction. Where this carbon is going to end up slightly positive, this hydrogen is going to end up slightly positive, this oxygen is going to end up slightly negative. Permanent dipole moment. So that was 2 that have permanent dipole moments. Let's try PO43 minus. You all try it first. As a reminder, we did the Lewis structure for PO43 minus about 30 minutes ago. So if you got here in the last 30 minutes, you missed that part, but try it. I'm going to erase this bit. Was that good? Did that make sense to you? While everyone's working on that, were there individual questions people wanted to talk to me about? Okay.
Personal questions?
Yeah.
Yeah, I just wanted to follow up on like my quiz opening extension, maybe like after this.
Oh yeah. Did you email me?
I emailed you about
Okay.
it, yeah. I just feel like, yeah.
Yeah, we'll talk about it.
Exactly.
symmetric.
Okay. Let's see. Yeah. So is it going to end up being polar or non-polar? Is that geometry symmetric or not?
Symmetric?
So?
It's not.
There we go. Okay. So it seems like people are getting on track with this. Actually, let me check one more person because this was one of your questions. Looks good. Ooh, symmetric or not symmetric?
This?
Well, this is what it would look like in 3D. Is that symmetric?
Yeah.
So it would be?
Yeah.
Yeah.
It has to be both electronegative and symmetric.
Yeah, it has to be both electronegative and not symmetric.
I know I got mine wrong apparently since it's not symmetric, but
No.
I got stuck on the geometry part, right?
No, what everyone is kind of getting thrown off by is that double bond. Right? You see the double bond and you're like, oh, that's not symmetric. But we're looking at the electronegativity. So when we look at phosphate, this would be, right, and this also has to do with the idea of resonance structures. Right? So people are drawing this and they're like, is this symmetric or not? In terms of the electronegativity. So when I look at this, first off, I drew it flat, and that's terrible. So let me go ahead and redraw it as like a tetrahedral. This is the little like chicken foot tetrahedral that people like to do as well. It's just a little like, wow. Right? So when we look at this, there is bond polarity between the phosphorus and the oxygen, because oxygen is
Electronegative.
second most electronegative, right behind fluorine. Right? And then the question is that symmetric? Is that difference in electronegativity symmetric around the center? And I have a hard time seeing it with my drawings, which is why I like to use a model kit. And so when I see this, I'm like, oh wait, that is a very symmetric shape. Right? Since that's a symmetric shape, I've got my difference in electronegativity, but I don't have my asymmetry. So this one is nonpolar.
Not even sideways?
Not even sideways. Right? And that's because of the way I drew it versus the way it actually is. Right? I have to, like, in my mind, when I draw this, I see this. Like, three-dimensionally. Right? And so the side to side cancel each other out. The front to back, you know, if you look at this, no matter how I spin it, it kind of looks the same. It's got high symmetry.
Yeah, so I can see where it would be symmetrical vertically. It's just sideways. I see that there's 3 below and 1 on top. So.
But the 3 below aren't going straight down. They're going to the sides, right? So
Okay,
watch this,
sure.
right? So here's my top, real quick. Now that's my top. Does that look different?
No.
What if I make that my top? Right? It's still symmetric.
Sure.
It's just that it's that detail of that three-dimensional symmetry when we have to worry about that tetrahedral shape. Tetrahedrals actually have quite a bit of symmetry to them. So that one ends up being nonpolar, even though it's got big differences in electronegativity. The double bond doesn't really matter, right? It's where's the electronegativity, and is that difference in electronegativity symmetric or not? Let's see. That's number 3. I'll do one more. So 2, 4, or 5. Which one should I do?
5.
I'm seeing 4
Yeah.
and 5.
5.
Yeah, okay, 5? Okay, let's do number 5 real quick. Big challenge with number 5 is making sure we draw the structure correctly. So take a moment, try to draw the structure. I'm going to give you about a 30-second head start. Should probably give you more. I'm going to count my electrons. Chlorine brings 7. Oxygen brings 6 each, and I've got 3 of them. That's going to be 18. Minus 1 brings me 1. So that's going to be 26 total. I'm going to put my least electronegative. Chlorine's not very... Chlorine's pretty electronegative, but it's lower than oxygen, so it goes in the middle. Put my oxygens around it. Try to get everything to 8. Eight, 16, 24, 26. Now there's going to be a lower state way to do this. This is pretty similar to what we saw with SO3, where I first drew it like this and I was like, oh, formal charge suggests there's a better way to do it. And we can tell if I look at the formal charge of that chlorine in the middle, I'm going to have 7 minus 2 minus a half of 6. Oh, math. Oh, goodness. -2 is super bad. -2 or +2? +2. Still bad, right? Remember, formal charge greater than or less, like greater than 1 is not likely. So this structure that I drew is not very likely. I can use another hint that I don't know if you all have picked up on this. Remember, the important part that I recommend everyone does is, if you look at like, oh, what I do for ClO3 is different than S2O3, is different than CO3 is different than, right? This is actually the same process over and over and over again. And so it's making sure that we're paying attention to those overarching ideas of how these things relate to each other. One of the things you might have noticed is, for these oxo anions, the minus charge almost always relates to the number of single bonded oxygens. So I can erase that, erase that, with that. Now I'm going to have 7 minus 2 minus 10. That will get me a 0. And I've only got 1 minus on that 1 oxygen. I've minimized my formal charge. I've got as many zeros as possible. I've only got 1 minus 1, which corresponds to that minus 1. Great! That's only the beginning of the problem, because the problem was asking us what's the permanent dipole moment. So the first thing we have to be able to do is draw these Lewis structures. After we've got this nice Lewis structure, then we can go ahead and put in the geometry of it. Trigonal pyramid. Difference in electronegativity. This actually looks a lot like SO3 2-. Oh, I forgot one of my double bonds. This looks a lot like SO3 2-. I've got that difference in electronegativity. I'm probably drawing those too big because chlorine's pretty electronegative. Chlorine and oxygen are pretty similar. But because I've got that asymmetry, I've probably got a little dipole moment towards the oxygen. I don't think it's going to be that big because the difference in electronegativity between chlorine and oxygen is pretty small. But still, it's going to have a permanent dipole moment.
So then what makes it a polar bond or a non-polar bond? What's the exact definition for that?
A polar bond is when you have two things bonded to each other with a difference in electronegativity between them.
Of how much? Like.
So we don't get into the specific numerical values of how big the difference in electronegativity is.
I thought it was like 0.4, but.
0.4, 0.5. But like, I don't expect anyone to memorize the electronegativity values, right? So we're mostly looking for like periodic trends, obvious cases. So if we're looking at the periodic table, I lost my periodic table again. There's like a pile behind me. Oh no, they're just right behind you, Beverly. Oh, even, yeah, that works.
This one?
Yeah, sure. Perfect. Okay, so if we're looking at this, oxygen, fluorine, and chlorine kind of make that top corner. And so they're all very high electronegativity. Oxygen, fluorine is most electronegative. Oxygen is second. Chlorine's a close third. And then as you step away from that, nitrogen, sulfur, and bromine are kind of the fourth place ones. And they're all like nitrogen, and it's kind of like nitrogen is less, sulfur's a bit more, bromine's a bit less again. So there's kind of that trend. And I don't even know for sure. Like, I'd have to look at the numbers. But we're looking for those like obvious differences. A lot of times we're looking at oxygen to things, And oxygen is always more electronegative than the things it's attached to, unless we throw fluorine in there, which would be weird.
Okay. So like the bond's polar.
Yeah.
Okay.
The bonds end up polar. The extra bit of saying, oh, it's probably not very polar, that's me kind of demonstrating a little bit of advanced thinking that I normally wouldn't ask, right? The question is just, is it polar or does it have a permanent dipole moment or not? And the answer is, yes, it has a permanent dipole moment. But if we want to do that deeper thinking, we can also say, whoa, how big is that permanent dipole moment? I don't have a specific number to it unless I look it up in Models 360 and get the exact debye of the dipole moment. But I'm guessing it's not going to be very big because the difference in electronegativity kind of small, right? Chlorine and oxygen are both pretty electronegative. Also, this stuff is pretty reactive. Having chlorine and oxygen bonded to each other like that. Perchloric acid, very dangerous. Good on. So this kind of covered a lot of the concepts we wanted to talk about. The difference in electronegativity, the molecular shape, this idea of polarity, looking at bond dipoles to get permanent dipole moments. It was also covering number 26. Any other details we want to talk about in that collection of ideas?
Maybe a side thought. I haven't really seen anything in the middle of the periodic table mixed with oxygen. I don't even know if you're able to do that, but
Not so. You notice most of the things we are doing here, we're only doing non-metals because we're looking at covalent bonds.
Yeah.
If we're looking at the center of the periodic table, that's all metals.
Yeah.
So you'd be looking at ionic bonds, and so you'd have the difference in electronegativity so large that it would be ionic bonding, not covalent bond.
Yeah.
So you wouldn't talk about permanent dipole moments in that case, you'd be talking about ions.
Gotcha. Fair enough.
Until we get to Chem 129 and we do some really weird compounds. But that's a special case, special case. Okay. Do we remember who put 6.1 number 8? Does anyone still want to see 6.1 number 8?
I think that was just an example.
Otherwise, we'll move on to 6.2, talking about IMS and boiling point. Okay. Have I told you lately I don't like whiteboards? I don't like whiteboards.
You prefer chalkboards?
Yeah. Because I don't like the ink. It's like everyone's like, oh, chalkboards are clean. It's like, yeah, you get chalk on you, but it washes off easy. This is like all this stuff like stains my clothes and things like that. And staining the floor here because this is where my whiteboard's been for like 2 years. And it's just a different mess. In any case, we are looking at 6.2, and we're just going to run the full gamut of 21 to 26, which is the organization of 9 structures into their order of boiling point. Does anyone have that up?
What? 6.2?
6.2. Okay, yeah, I just want to write all the structures real quick on the board. Yeah, if you can hold it just like that for a second, that'd be great.
Oh.
How am I going to fit this all on here? So we got all of these structures, A through, and I would encourage you to look at your problems on your screens because I feel like this is a little chunky and I couldn't fit them all in very well and give myself enough space to do the problem. And what this problem essentially asks us to do is put all 9 of these compounds in order of boiling point, from lowest to highest. And then it breaks it up, instead of just doing, you know, like one problem where it says do all 9 at once, it kind of breaks it up into a couple of thinking steps, which is why this is 21 through 26. 26 is now do all 9, but it breaks it up into little thinking steps of, okay, let's start with the first thing of what's going to have the highest boiling point. Well, let's first talk about what gives rise to the difference. Let me move this down here. I'm going to give myself a little bit more space. I did forget to talk about something. Got to talk about precipitation reactions still. Hey. So, what are the things we consider when we're looking at boiling point?
IMFs.
IMFs and
Molecular weight.
molecular weight. Right, when we're looking at the IMFs, we're going to look at 3 different steps. So even though I say what are the 2 things, it's really what are the 4 things, because it's molecular weight and the 3 IMFs. We're going to look at London dispersion force, which is going to be a surface area consideration. We're going to look at dipole-dipole interaction, which is going to depend on that difference in electronegativity and asymmetry, but let's just focus on the difference in electronegativity. And then we're going to focus, and then we're going to have hydrogen bonding force. We're going to need a delta plus on hydrogen, and then we need something else on the other molecule. And so we're looking at this in terms of all of the different compounds. But that's going to be the different considerations we have. So really, if I want to do all 9 of these at once, if I wanted to do all 9 of these at once, I would calculate the masses of all of them, and then I would look at the intermolecular forces of all of them, and I would compare the different intermolecular forces. What this problem does is it kind of breaks that up. And the first thing I'm going to look for, so if I want to find the highest boiling point, I'm going to look for the thing that has the most intermolecular forces and the biggest mass. E has a pretty big mass, but weak intermolecular forces. G, kind of in between, pretty big mass, but no hydrogen bonding force. I here is a lower mass. It's got 1, 2, 3, 4 things that are kind of heavy. It's got 2 oxygens, 2 carbons. But it's got 2 places where it can do hydrogen bonding forces. So it's essentially got 2 counts on the hydrogen bonding force aspect. Question?
What was your thought process for like G and I to say like, oh, no hydrogen bonding force versus hydrogen bonding force? Is it because the H's are bonding to O?
Yeah. Right, so when I look at this one, and I find it easier, while the problem has it written down like this, I find it easier to actually think about it in terms of drawing the Lewis structures for all of these, because I find that easier to see. So let me redraw this one with its Lewis structure. And then we'll draw this one with its Lewis structure. And I find the line angle drawings is easier to think about for, oh, I just forgot what that one was. How many carbons was it?
E was
CH3, CH2, CH, CH3, CH2, CH. Okay. Right, and so I find it easier to see, like I've done this problem enough times. I actually helped somebody with it earlier before office hours. And so I already kind of had the Lewis structures in mind, but it's easier for me if I have everything in line angle drawings, right? So when I'm looking for hydrogen bonding forces, it's like I can do hydrogen bonding forces and B can do hydrogen bonding forces. In terms of masses, they're all in the same ballpark. They all end up in the same ballpark of their masses. So I don't think mass is going to be a big consideration for any of these. Right? This one, a little bit bigger mass. This one, a little bit smaller mass. This one with the chlorine's pretty heavy. So this one ends up, even though it's a smaller molecule, smaller surface area, it's actually not that much smaller in mass. So I don't think mass is going to be a huge consideration for any of these. So I'm going to start looking for my different intermolecular forces. I think B and I are the two best candidates for the highest boiling point. Since this has two spots where hydrogen bonding force can happen, I think I is going to be highest. Right? And that's the first problem. The first problem, 21, is just like, which one's highest? 22, which one's lowest? I've got that right, correct? I mean, in terms of which numbers it is and what it's asking. Number 2 asks which one is lowest. So if I'm going to go for lowest, I'm going to want the one that doesn't have strong intermolecular forces. So I'm looking at E and F. Right? Both of these things are just hydrogens and carbons. No hydrogen bonding force, no dipole-dipole moment. And between those two, it's just going to be the one we're looking at limited dispersion for. So it's between E and F, which one has the smaller surface area. F is going to have the smaller surface area because more branching usually leads to less surface area. Then we get into the kind of interesting things. And there's some extra thinking we can do here. Where number 23 says, okay, now I'm going to pick 3 of these and ask you to consider what's happening with these 3. But before we even look at which 3 it's going to do, we can look at these and start saying, hey, how would I, if I was going to do all 9 of these, mass isn't a big consideration, how would I start clumping things together? If I wanted to look at which ones had similarities, what would I consider?
Ones with only CH.
Ones with only CH, right? So I can look at E and F are pretty closely related to each other. Maybe C as well, because that one doesn't have any oxygens. Everything else besides those 3 have oxygens. So maybe C, and we'll double check that in a moment. What else do we know? So what other things are there that are similar?
A lot of them are dipole-dipole, but no hydrogen bonding.
Which ones?
Probably this one right here.
Yeah?
That one is hydrogen bonding.
A, G, H, and D,
Yeah.
right? So we could group all those together. There's an even better separation we could do. Notice G, H, and A are all ethers, right? They have the same functional group. They've got the oxygen in the middle, oxygen in the middle, oxygen in the middle. So those are all going to have really good similarities. And then we've got the last ones. We've got I and B go together really well. And D is kind of a weird one. It could fit in that group, or it could fit in this group. Right? Because you're right, it doesn't have hydrogen bonding force, but it's also not an ether. So it's like, which group do I put it in? Now, since the other groups already have 3, we'll probably put it in the orange group, so it also has 3 in that group. But now we kind of look at number 23, and 23 says,
rank from lowest to highest boiling point for A, G, and H.
look at that. It's one of the groups we created, right? By looking at the similarities and differences in the structures, even before we read number 23, or maybe after 23, we can look and say, hey, why'd they put A, G, and H together? And we're like, oh, ether, ether, ether. The only difference between them? Amount of branching, right? No branching, little branching, lots of branching, right? So we can say, look, these all with the oxygen in the middle between 2 carbons, the dipole moments are approximately the same. They're also all isomers of each other. They have the same number of carbons, hydrogens, and oxygens. So mass is not a consideration. Dipole moments about the same. There's no hydrogen bonding force. The only thing that matters through A, G, and H is the amount of surface area. So in that consideration, H is going to be the highest. G and A, that's a little tricky. Which one? Now, it's extra tricky because I didn't draw them to scale. Like, I had more space when I drew A, so it looks bigger than G. But also, in terms of spacing, in terms of branching, because this thing has the 2 branches on the side and this one has a little bit of an extra wiggle to it, I'm going to guess that G goes first. Not guess, but I'm going to determine that G goes first and A goes second. Just because that extra branching that I see in G. And one of the ways you can do that is you can look for your longest chain. So So this goes, the longest chain here is like that. The longest chain here is like that. So 1, 2, 3, 4, 5 things across. 1, 2, 3, kind of the same. But this one, I think it's just going to end up a little bit bigger. That oxygen's a little bit more off to the side. I think A is going to end up with a little bit better intermolecular force interactions. Does that make sense? Number 24 gives us another set of 3. Question?
Before we move on, when you said one of these has more branching, should we like go and circle the amount of branching and determine which one has more, or is it just like we look?
It's more, at this point, we're doing mostly a qualitative kind of assessment. And this gets into when you were asking about IMF magnitudes, right? So when we talk about the magnitudes, the intermolecular forces, if you remember, I drew it where each one has a certain range of possibilities. And in order to get to the exact magnitudes of how strong these intermolecular forces are with each other, we would have to go to the energetic interactions on a scale of kilojoules per mole and get the exact numerical values associated with it, which we can do. And we look into that some degree in Chem 128 when we start looking at the enthalpies of reactions, the delta H, which is how we quantify the total amount of interactions, not just the bond energies, but also the intermolecular force energies. And so we can get into specific numbers for that. Right now in this class, without getting into the whole idea of enthalpy, entropy, and Gibbs free energy, we just kind of say, hey, we can see that, you know, we've got more spread out, we've got less spread out, we've got more surface area, a little bit less surface area.
Sure. So too in depth for the.
Yeah, you know, and honestly, like G and A, if this was on an exam, G and A versus A and G, like the order of these two, I would say they're approximately the same. And for me, what would get you the points is not the order you put them in, but the argument for why you put them in an order. So being able to look at it and say, oh, I know it depends on surface area, and by my estimation, if you say G has more surface area, but that's why you're putting it in a different order, that logic, that thinking, that's what gets you the credit.
Sure. Thank you.
If you get them in the right order, if you're like GAH because mass, that's not going to get you the credit. Even though your order's correct, your reasoning is wrong. And that's going to not give you full credit. Okay, so 24 says, hey, now put these next 3 in order. And it's?
B, D, and I.
B, D, I. So that's going to be, okay, so they did put D into the orange group. That's our orange group. And we already know I is going to be the highest because we already got number 21 correct. We also see 2 instances of hydrogen bonding force, really strong. B is going to be second to last because it's got 1 instance of hydrogen bonding. D, with no hydrogen bonding, is going to have the lowest in that set. Right? And that set was a little bit easier to do because it's dipole moment, 1 hydrogen bonding force site, 2 hydrogen bonding force sites. The extra hydrogen bonding force possibilities makes it so it's more difficult to boil, more energetic interactions to overcome. Number 25, I'm guessing, is going to be CEF. Because it's the only 3 that are left. Now, we already said that F was going to be last. And then it's just which is second, C or E. And the thing we have to remember is C. Actually, it feels weird to me to have C in this set because when I look at C, it has a dipole moment. Again, my drawing is not that great, and I keep losing my molecules. Ah, here it is. I'm losing my molecules. Right, so my 3-dimensional drawing is not that great, but this is what I'm trying to draw. The chlorines, no matter how I rotate this, end up on the same side together. And if you're like, well, what if we move the chlorine? Because of the symmetry, moving the chlorine doesn't really change the situation. So this thing is going to have a dipole moment towards the chlorines, because the chlorines are more electronegative than carbon. So in that situation, I think C is going to be last, highest boiling point in this set, and that puts E in the middle. You know, more branching, less branching. These two are isomers of each other. They're both 5 carbons. This one is different, but it has that dipole moment, so it ends up higher. Finally, number 26 says put all of these in order. We've already got them in chunks, and the chunks aren't random. It didn't randomly pick like, oh, do these 3 random ones and figure it out. It chunked them intentionally, whereas like, hey, G, A, and H all had things in common. D, B, and I all had things in common. F, E, and C all had things in common. Since we already know that F is the lowest, I can go ahead and say, look, that FEC set is going to be the first set. That DBI set, since I is the highest, that DBI set is going to be last. And then that GAH set is going to be in the middle. Now, you could make arguments. You could say, okay, I get the individual bits, but what if this order of C and G should change? What if this order of H and D should change? Possible, a little bit more nuanced, but if we look at D compared to H, we've got something with a relatively strong dipole moment and lots of surface area compared to something with a weaker dipole moment, still lots of surface area. So I think the order between D and H is correct. Looking at C and G, ooh, that one's a bit trickier. They're both pretty heavy. We've got the dipole moment, we've got the weaker dipole moment. I think there's some argument that C and G might change order, but there's not enough information to really make that distinction. So I think this order is close enough. Now, there was a lot of thinking inside of there, right? Notice we had to get the Lewis structures, we had to identify the intermolecular forces, recognizing the functional groups actually help us figure out the similarities and differences that we're going to see in the intermolecular forces. Similar functional groups have similar intermolecular forces associated with them. So we've got all of those different things that we can consider and put together. Is that good for? So there were 3. I paused because there were 2 different topics down here that related to this 6.2 problem, and that was the IMF magnitude, which I think we discussed, and then also boiling point ordering, which this problem was all about. Other questions on that before we get into one last conceptual idea? What time is it? Oh, we still got time. Ends at 4, right? Okay. So, any other questions on this? Okay. Let's go ahead and talk about precipitation reactions, how we write net ionic equations. And then I get to take a nap. It's been a long day. I probably don't get to take a nap, but you know what I mean. Okay. So precipitation reactions, right? The basis of precipitation reactions is when we put 2 things into water, usually 2 ionic compounds. So I'll do the one that we did in class yesterday, just as a reminder. We put 2 things into water. We start out with saying, hey, is sodium chloride aqueous or solid? Sodium compounds are? Aqueous. They're always aqueous, so that's aqueous. Nitrate compounds are? That's going to be aqueous as well. So then we say, okay, well, I mix these 2 things together. Technically, this is like looking at an Na plus a Cl minus, an Ag plus an NO3 minus. And I mix these 2 things together. I mix this sodium chloride solution with the silver nitrate solution, tumble it around for a bit, shake it up a bit, and say, well, what happens? And the silver, if it bumps into nitrate, same thing that we already had, just kind of the water, it will not interact with it. It would rather interact with the water. Bumps into the sodium, it's plus and plus, they're just going to push away from each other. Bumps into the chloride, something new and interesting. And that's what gave us this idea of the double displacement reaction for our medium fancy, which is appropriate for Cal Poly, or our simple flip-flop reaction where you're just flipping and flopping your cations. Right, so I just trade my cation positions. I do AgCl and I do NaNO3. Also, oh, no parenthesis there. Also, make sure you're doing this. It's unusual to do it down the board like this. You usually do it across the paper. I'm just doing it this way because I don't have enough space on the board. Now, I go through these compounds and I say, did something change? When this silver and this chloride bump into each other, do they stick to each other through the different kind of lattice energy forces versus water ion dipole interactions, or do they interact with the water and stay aqueous? Now, there are energetic arguments we can get into, and we do get into in Chem 128 again, but for us, we're just looking at the solubility rules and saying, hey, generally, yes or no. Generally, silver chloride is solid, sodium nitrate, aqueous. So we look at this and we say, okay, we did our flip-flop, we used our solubility rules, we can tell which thing is going to be solid, which thing is going to be aqueous. And then that's it for the reaction. Now if we want to do the net ionic, we have to do some extra consideration. Silver chloride stays still. Sodium nitrate would actually be the same as Na plus NO3 minus. And now I'm going to go ahead and cross out anything that's the same on my reactant side before they mixed and my product side after they mixed. Anything that's exactly the same elements, same charge, same state of matter, that goes away as a spectator. Sodium plus aqueous, NO3 minus aqueous, NO3 minus aqueous. My net ionic focuses in on just those things that are changing. So we end up with Ag plus aqueous plus Cl minus aqueous goes to AgCl solid. And what the net ionic equation tells us at its core is, I don't really know how silver ions got into solution, and I don't really know how chloride ions got into solution, but I can tell you if those things bump into each other, they form a solid. And that's going to be the interesting change in this. When I pour these two things together, the only thing that's going to be an interesting change is when silver and chloride bump into each other and start to form a solid. And we'll see that tomorrow in class because we actually get to start mixing things together and watch things happen. Ready for more questions?
Yeah.
Question, yes.
How do you know what is like solid and what is like...
Solubility rules.
Okay, never mind.
Wrong equation sheet, not on that one.
Okay.
Right, so we're going to use that soluble ionic compounds list and that insoluble ionics compound list. I just knew this one because we did it yesterday in class.
So when you're crossing the stuff out, how do you determine what you cross out again?
There's three things I look for. Same elements. I see people writing down, so I'm going slower. Same elements, same charge, same state of matter. If those three things are the same between the reactants and the products before the mixing and after the mixing, before the arrow, after the arrow, same elements, same charge, same state of matter, it didn't change. It's a spectator, and we get rid of spectators.
And it has to be like all three of them.
All three of them have to be the same. If any one of those things change, something's changed. One more example. Okay. Let's see if I can make a. Can you hand me one of the other equation sheets way behind you?
Dr.
Yeah.
I had a problem I wanted to ask that's related to precipitation.
Oh, cool. Yeah, let's get that problem first.
It's off the first prep activity. So it's lead-2 nitrate plus potassium iodide. Is that made into solid lead-2 iodide plus potassium nitrate.
Okay.
And then it's asking for the reactants and the products.
For the net ionic?
Yeah, the net ionic.
Okay, so a couple things we have to be careful about. First, I've got to get my states of matter on there correctly. Okay, so it's going to look something like this. Now, we have to be careful. We haven't talked about balancing chemical reactions yet, but that's one of the first things we're going to do in class tomorrow.
Yeah.
Is making sure that we don't create or destroy anything. So here are the things we have to look for. I got to give myself a little bit more space here. Right, it told us solid lead iodide, so I know that it's solid. That's why I did that. Oh, man. Every office hours, it's just like ink. In any case, what's this supposed to be an NO3, not an NO2? So anything we look at here, when we're looking between the two, I need to have good compounds, and then I need to have the same number of each element in the reactants and the products. Because chemistry at its core, I know we always talk about making things with chemistry. Chemistry doesn't really create new matter. It rearranges matter that's already there, right? So all of the nitrogens that are here before I mix have to end up someplace here after I mix. All of the potassiums that are here before I mix have to be someplace here after I mix. Is it asking for the reaction or the net ionic?
Well, one of them is the net ionic, but it's also asking for the the coefficients and the formulas and the
Okay.
reactions, yeah.
So let's go ahead and let's get the coefficients and the formulas and everything. Now, step one is making good ionic compounds, which means they are charge balanced and stable. So here, lead had that +2 charge. We've talked about this a little bit in the past. Nitrate has that -1 charge. So how many nitrates do I need to stabilize it? 2. After I've got that subscript for the stable compound, I don't change the subscripts anymore. I do the same thing over here with the lead iodide. The lead is in a +2 state. The iodide is in a -1. How many iodides do I need to make a stable compound? 2. After I've got that subscript for how many iodides are attached to the lead, I don't change my subscripts. Now, when I'm looking at this, though, I have 2 iodides in my product and only 1 in my reactants. So the way I fix that, after my compounds are good, I don't want to change my compounds. They're all stable. They're all good compounds. But I can change my coefficient of how many potassium iodides are involved in the reaction. So if I've got 2 potassium iodides, that's going to give me 2 K pluses and 2 I minuses. That'll take care of, now I've got 2 I minuses, 2 I minuses, 1 lead, 1 lead. But now I've got this problem where I've got 2 K pluses. I've only got 1 K plus. But I've also got 2 nitrates over here and only 1 nitrate over here. So a 2 in front there gives me 2 potassiums, 2 potassiums, 2 nitrates, 2 nitrates, 2 iodides, 1 lead, 1 lead. And I often recommend, well, when we're first doing this, we can make like a little table of what's going on. Where I keep track of my lead, my nitrogen, my oxygen, my potassium, my iodide, and make sure I've got the same numbers. Lead is easy. I've got 1 of my reactants. I got 1 of my products. Great. My nitrogen, I've got 2 NO3s here, so that's going to give me 2 nitrates. I got 2 NO3s here, so that gives me 2 nitrogens in my nitrates. I've got 6 oxygens, 6 oxygens. Potassium, 2 potassiums, 2 potassiums. Iodide, 2 iodides, 2 iodides. Same number of things from my reactants to my products. And again, we haven't done this in class yet. We're getting a little bit ahead, but that's a good thing.
This is stoichiometry, right?
This is balancing chemical reactions, which is the step before stoichiometry. Well, it's the first step in stoichiometry. First step in stoichiometry is getting a balanced chemical reaction. So now, so that's our balanced chemical reaction. How do we get this to net ionic? So this aqueous thing, this lead nitrate, is going to go to Pb2 plus 2 NO3 minus. Right? It's not 2 nitrates. It's not 1 NO3 it's 2 nitrates.
Yeah.
Remembering that it's a crystal structure with a lead and a nitrate and a nitrate. Potassium iodide, I'm going to have 2 potassium iodides that both break apart, so I'm going to have 2 K plus, and I'm going to have 2 I minus. Come down here, my lead iodide doesn't break apart because it's a solid. Check my solubility rules to make sure that's true. And also the problem told us it's a solid. So good hint there. My potassium nitrate becomes 2K plus 2 NO3 minus. Then I start looking at I start looking for spectators. Potassium, I've got 2 of them. They're both potassium, they're both plus. I didn't write down aqueous, but they're both aqueous as well, so that's gone. Nitrates, right? The easy way to look for your spectator ions, look for the product that's aqueous, because it's not, the solids aren't going to be spectators, right? That's changed state for sure. So I look at my aqueous product, I check my potassium, I check my nitrate. 2 nitrates, NO3, -1 charge, 2 of them, gone, gone. That means my net ionic is going to be Pb2 plus aqueous plus 2I minus aqueous goes to PbI2 solid.
I really understand what net ionic is, or what we're trying to look for when you're doing that. I understand how you're doing it, but like.
Why? So
What
again,
is
it's trying to get rid of some of the clutter and really focus in on just what's chemically changing, right? The nitrate and the potassium are not changing at all. They're the same on the reactant side as the product side. It's K plus and K plus. It hasn't changed. It hasn't done anything. This allows us to focus in on what's chemically changing. And so when we start to emphasize, well, what's actually happening, then that ionic allows us to focus in on what's actually happening, what's actually changing. Becomes really useful in future classes as well, because when we start looking at how much this reaction happens, the potassium and nitrate don't need to be considered. I can just focus in on this as my net ionic precipitation reaction.
But also aren't some of the other things also changing because they're bonding to new things, like I forgot what K is, and nitrate.
Potassium.
Potassium
The
and
potassium, and that's the thing that's not actually happening, right? So we write it as KNO3, but that KNO3, since aqueous, is actually K pluses and NO3 minuses.
All in water?
All in water.
Okay.
Just like it was in the reactant side.
Oh, okay.
So it's actually not changing, which is why it's good to eliminate it as a spectator. And it allows us to really see, oh, these are the only things that are actually changing.
Makes sense.
Cool. Okay, that's it for office hours. I'm going to go ahead and stop recording. Sorry about the video. It's like